unusual behavior of water. Okay, liquids generally, okay, increase in volume with increasing of the temperature, and has the average coefficient of volume expansion normally about 10 times greater than those of solids forms. Okay, water basically or generally follow this kind of behavior. But then there is an exception whenever the temperature of the water near to zero, okay, near to zero, the behavior of the water slightly different compared to the rest of the portion of it. Right, so if we zoom this part or magnify this part, if you see here, okay, this is part linear, okay, which is in comparison to this, okay. So this is the part which is slightly different. That is what we call it unusual behavior of water. So here, what happened actually, okay, as the temperature increases from 0 to 4 degree, right, to 4 degree, okay, water contracts and its density therefore decreases. Okay, so what happened in this temperature? Water is contracting. Okay, and therefore, okay, its density will be increased. Right, above 4 degrees Celsius, okay, above of this, okay, water expand normally. Okay, rho is equivalent to m over v. Okay, with the increment of temperature, okay, volume is increasing. Volume going to be increasing with the increasing of temperature. Okay, therefore the density will be decreasing. Rho maximum of water is 1.000 gram per centimeter cube, or you may put it as 1000, okay, kilogram per meter cube, okay, rho maximum. When this happened only at T equivalent to 4 degrees Celsius. We can use this unusual thermal expansion behavior of water to explain why pond begins freezing at the surface rather than at the bottom. So, for example, in this situation, when the air temperature of the surrounding, right, drops, for example, 7 to 6 degree, the surface water cools down, right, and consequently decrease in volume. When it decrease in volume, rho is equivalent to m over v. Okay, when the T is dropping, the volume will be decreasing. Therefore, the rho will be increasing. Okay, what will happen? The surface water will be denser than the water below, which has not cooled and decreased in volume yet. As a result, the water surface will sink, and warmer water from below portion of will move to the surface, okay, replacing the denser water just now. When the temperature is between 4 to 0 degrees Celsius, this is happen, let's say 7 degrees Celsius to 6 degrees Celsius. Okay. Now, when the temperature is 4 degrees Celsius to 0 degrees Celsius, what will happen? The surface water expand because the unusual behavior just now. Okay, so in this part, okay, okay, the water is expanding. Okay, so the surface water expand as it cools, becoming less dense. The whole situation will be in opposite to this. Less dense than the water below it. The mixing process stops. Okay, and eventually the surface water will freeze. As the water freezes, the ice remains on the surface because ice is less dense than water. The ice continues to build up on the surface while water near the bottom remains at 4 degrees Celsius. If there were not the case, fish and other forms of marine life would not survive. Everything going to be freezed. This is the Sunnatullah, how brilliant Allah Ta'ala create the behavior of water. As we know, the earth containing more than 70% of water. So now, okay, this is macroscopic description of an ideal gas. So just now we've taken a look on the liquid. The volume expansion that we have learned, okay, previously in equation delta V equivalent to beta V initial delta T, this is equation 18.7, is based on assumption that the material has initial volume V initial before the temperature change occurs. Right. Such in case, okay, for solid and liquids, because a sample of solid or liquid has a fixed volume at a given temperature. The case of gases is completely different. Okay, the interatomic forces within gases are very weak because the arrangement of the molecule within the gases will be far from each other. Let's say this is, we have a closed container. If we have an atom of gases, they are placed randomly and far from each other. So they are not communicating or interacting, okay, in similar method compared to the solid or liquid within the neighboring atom. Therefore, there is no equilibrium separation for the atom and no standard volume at a given temperature. The volume depends on the size of the container, right? As a result, we cannot express the change in volume in a process on a gas with this equation, because we have no defined volume initial at the beginning of the process. Equation involving gases contain the volume V rather than the change in volume, because here we have change in volume from an initial value as a variable. Okay, so we cannot simply use this one for gases in conclusion. For gas, it is useful to know how the quantities volume, V, P, okay, and temperature T are related for sample of gas of mass M. Alright, in general, the equation that interrelated to these three quantities are called as equation of states. So if you see hot air balloon here, okay, the volume of it fixed. Okay, so we simply cannot use this one. This one not valid for the situation of the gases, because normally in gas, okay, the volume of it will according to the volume of the container. So the equation of states actually is the combination of the ideal gas law from these three laws: Boyle's law, Charles' law, and Gay-Lussac's law. So let's recall, you've learned this one, okay, from your primary school. So Boyle's law talking about volume is inversely proportional to the pressure. Consider the T is constant because we have three elements to be considered in gases case, which is temperature, pressure, and volume. Okay, so for Boyle's law, P and V is inversely proportional to each other. Okay, so P is inversely proportional to the volume with the consideration of temperature is constant. Right, for Charles' law, volume is directly proportional to the temperature. Volume is directly proportional to the T with the consideration a condition of the pressure is constant. For Gay-Lussac's law, okay, pressure is directly proportional to the temperature in Kelvin. Pressure is directly proportional to the T in Kelvin, with the condition that here it must be what constant? volume must be constant. Right. So combining these three laws, okay, will give us the ideal gas law, or we also name it as equation of states. Actually, the equation of state is very complicated. However, it can be simplified or considered as this one whenever we consider the gas that we are looking at is the ideal gas. Okay, so what does that mean by ideal gas? The gas has low density. The separation distance between the neighboring atoms is very far away. So the communication or the weak interact between the neighboring is very low. So this is some assumption for ideal gas. So the model that we're going to use for derivation, for calculation in this topic will be ideal gas model, right? To make this equation become simple as it is. Okay, so we have PV equivalent to nRT. So P is the pressure in Pascal or Newton per meter squared. V is volume in meter cube. N is number of mole, right? R is universal gas constant, and T must be in Kelvin, temperature in Kelvin. So N here, okay, is equivalent number of mole, equivalent mass of substance over molar mass of the substance or gas itself. Okay, so this is the meaning of 1 mole. So what is mole? Mole is actually a unit, okay, because we are dealing with a gas, okay, where the number molecule of the gases is numerous. Okay, therefore we need instead of gram or kilogram, we also may use the unit of mole. So 1 mole is considered as a container, a unit, displaying within 1 mole how many atoms exist. Okay, that is the meaning of 1 mole. Okay, and R is 8.314 joule per mole dot Kelvin. But if you are using the V in liter, the P in atm, the N in mole, and the T in Kelvin, you may use this one as well. Right. So our ideal gas law just now, PV equivalent to nRT, also can be manipulated or rearranged in terms of Boltzmann by using Boltzmann constant, where we know Boltzmann constant, the Kb is equivalent to R over Na. R is universal gas constant over Avogadro number. So how they rearrange this is PV equivalent to nRT. The N here is replaced with N over Na. N is number of the molecules. And then you have R over Na is the Kb. This is your Kb, Boltzmann constant. Right, so the equation now may rearrange in terms of this PV equivalent to NKBT. So you have two options, whether you want to use this or you also may put it like this, either. Okay, so doesn't matter actually. So P, V, and T are known as thermodynamics variable. Okay, so thermodynamics variable. So example 18.4, heating a spray can. A spray can containing a propellant gas at twice atmospheric pressure, which is 202 kilopascal. It is then tossed into an open fire. Okay, please do not carry out this experiment. Okay, it's very dangerous. It's going to explode. When the temperature of the gas in the can reach 195 degrees Celsius, what is the pressure inside the can? Assume any change in the volume of the can is negligible, so fixed volume, okay? So PV equivalent to nRT. So we have rearrange PV over T equivalent to nR. Okay, we know that this is constant for the very beginning of the situation at 22 degrees Celsius, and R is the same, to the situation when it reached 195 degrees Celsius. Therefore, we can have a ratio. The NR initial situation is the same to the NR final situation. So that's why you can have a ratio like this. Right, so since the V is the same as well, right, this one also the same, so you are left with this, right? So now substitute everything, then you will get the final answer. Make sure the unit is the same. Then suppose we include a volume change due to thermal expansion of the steel can as the temperature increases. Does the alter our answer for the final pressure significantly? Okay, so now let's consider the thermal expansion for the can, the steel can, the container. Alright, so delta V equivalent to beta V initial delta T. The beta is 3 times alpha. Okay, so alpha for steel is 11 10 to the power of negative 6. And then volume initial 125. Okay, and delta T is 173 degrees Celsius. Then you are going to have 0.71 centimeter cube. Okay, this is the delta V. So by taking the equation that we have in our hand just now, P final, T final over T initial, V initial over V final times P initial. So as now we cannot cancel out the V because there is changes in V. So V initial over V final, okay, is equivalent to, this is V initial, this is V final. How to get V final? V initial plus delta V, because delta V is V final minus V initial. We want to have V final delta V plus V initial. That is how we get this, right? So you have 0.994. So it means only, okay, only 99 in terms of percentage is 99.4%. Okay, once you have this, okay, in terms of percentage is 99.4%. This result differ from equation 3 only in the factor of this amount, okay. Therefore, the final pressure will differ by only 0.6% from the value calculated without considering the thermal expansion of the can. So it means that, okay, 99.4 over 100 times the previous answer 320 kilopascal give us 318 kilopascal. So means that the difference is very small, okay, only 2 kilopascal. So this is assignment for you. Okay, the first one, the second one, the third one. That's it. Thank you for watching. Do not hesitate to ask any question regarding this lecture. And also, do not forget to upload to Google Classroom the 3 question or pop quizzes just now to our Google Classroom. Thank you.